only one question, sir.
Yeah. Yes.
Sir, only because I am PhD on antenna systems. Okay,
Huh.
I done my PhD on antenna systems. So basically, that will be microstrip antenna. You are talking about small size antenna means.
No, no, it could be any type antenna, and you will see some of the photographs of the antenna used for IoT. So if it is microstrip antenna, some of I mean some of the antennas you can broadly categorize as printed antenna because it
Yes,
may not be having the backing ground plane, so you cannot call this one as 100% microstrip configuration. You can say that PCB or printed circuit board antenna, and also WIP antennas are extensively used. That metallic structure which can be a little bit modified to make a loaded monopole antenna. So you will see the photograph of those antennas. So maybe for next 1.5 or next 1 hour and 15 minutes, it may be a little bit repetition for you. But nevertheless, we have to take whole class along. So with that, I will not skip the basics of antennas. I will still go ahead and cover the basic of these antennas. And I will not be specifically going for the design of the antenna. I mean, I'll tell you the basic principle, I mean, of the operational principle of this antenna. So that I would like to discuss, but as such, we will not go deeper into the design of these. You said microstrip antenna or dipole antenna. I will give the overall view of the antenna requirements for IoT. We will also discuss some of the basics of antenna so that you are able to correlate when I say that broad beam or omnidirectional pattern. Those things we will spend some time, and then we will come to the some of the antennas which are used for IoT. So is it okay? I mean, is that answers your question? Hello.
Yes, sir. Sir, you can go ahead, sir. Many
Okay.
participants are there, sir.
Okay.
Thank you.
So we'll start with the that introductory slide that this is the basic content of the talk. Internet of Things, you have been hearing lots of things about IoT. So this basic what do you call that schematic diagram which is put here gives you the overall view of that IoT, how it functions. So that we will deliberate very briefly. Then we will come to antenna characteristic, and I will try to correlate the antenna characteristic for IoT requirements. Then there are also requirement of the footprints of this antenna. This antenna has to be very efficient so that you don't lose the power in terms of efficiency, and most of the power which is being radiated or received should be for intended purpose. Then we will go for the definition of the gain, and then because these antennas operate in bounded media, you don't have unbounded media here. So lots of mutual coupling, interference, sort of near field coupling, all those issues are the main issues for these antennas, because that that electronics crowding, that is taking place now, because everything we want smart. So from that point of view, we will try to briefly discuss about the interference management. I mean, I'll introduce the concept, and then when we discuss about the antenna characteristic, this interference suppression, how to use these antennas in highly interfering environment where that you can say that intense EMI environment, electromagnetic interference environment. So this is what we will be covering in this lecture. Now this uh, if you I mean, if you want to know, let us say when Nagendra was introducing me, at that time many of you might have just Google search or just typed my name, and then in your mobile you could have seen that what is my background, what is was my present job, what was my past job. So that is what signifies that Internet of Thing. You know, all the informations, most of the informations, I would say that available in your fingertip through this that internet connection, and then most of these things you are able to access, and then in a very handy manner you are able to access this information. The network of the various subsystems operate when you type something on in your mobile phone, and that gets connected to various nodes, and then that is how you get information. Somewhere some information is stored, and that information you are able to access wirelessly. I'm emphasizing the word wirelessly, you know. So here various these things are shown here in this one, and then you can have a direct wireless most of the
Sir,
time.
sir, sorry to interrupt you, sir. I think
Yes,
your slide is not shared yet, sir.
it is not shared. I'll just check. Amar,
Sir, go to the present now.
yeah. I'll go that. Yes, present now your entire screen.
A window. Go to the A window, sir,
Yeah, now
and then
you are
you
able
select that PPT.
you are able to see now.
Sir, we are now you click on PPT, sir.
Yeah, so
Yes, sir. Now we are able to see, sir.
okay, it was not shared, it seems. No
Okay, sir.
problem. Okay. Yes. Slides from the beginning. Sorry, I thought you are already able to see what I am presenting. So it did not strike to me that I have to press that sharing button. Thank you for
No issue, sir. You please continue, sir.
yes. So the basic content I was telling that I have already elaborated these points, that we will come one by one. But what I was saying is that the most of the time, except barring some few cases, the mode of communication for IoT is wireless. You can have a direct a wireless connection between various nodes, or they can also be connected through internet, you know. So whenever that wireless requirement comes, like we are that IoT has become most relevant now when we are talking about a smart city, smart home, smart kitchen, smart library, smart institutes. These days people are talking about smart agriculture, then is smart warehouse, smart this sort of storage capacity. So you are able to access the information remotely through wirelessly, and they are linked, they are a part of various nodes, and they are interlinked through internet, so that you are able to access all the information wirelessly, you know. So when we talk about wireless technology, Then like if you compare the communication system with human body, uh, human body sees or communicate with outside world. He is able to access and then see outside world through his eyes, you know. So like that, for any electronic system or wireless system, antenna is the very very important subsystem, and through antenna it wireless system communicate directly or through some that base station or through some hub. They are able to communicate and then try to get all the information for us. So it is emphasized here that role of the antenna is very very important. Of course, other processing and then display, all those things are equally important, but for any wireless system it require antenna. So we will discuss in detail, starting from the basic definition of antenna. I mean, what is the function of the antenna, and then also parameters, various parameters of the antenna. So when we will refer to as whip antenna or printed circuit board antenna, PCB antenna, or in that matter, let us say wire antenna, you know, what will be the characteristic of that antenna, you will be able to appreciate that. So we will discuss in detail the basic parameter of antenna. Now let us say this, the man is standing here holding this antenna, and then you are putting, you want to communicate with this subsystem here, which is shown here. Now, if you have a desired radiation pattern and then sufficient amount of energy is getting radiated towards the point where you want to communicate wirelessly, then only this connection will be, wireless connection will be established. So it is very very important that the radiation pattern, and from there we derive lots of other parameters of the antenna, has to be designed according to the application. Now of another example which I will give, that let us say here you have a TV set here, and and then it's active TV set. Let us say that it is radiating as well as receiving, and then you don't, when you are making communication from this point to any of the subsystem, and this subsystem here is creating nuisance for your connectivity from here to the desired subsystem. So in that case, you have to optimize the radiation pattern in such a way that it has got minimum gain towards this interfering signal. So here, if you are able to I mean have a, for the base station, if you are able to have a tower with antenna array, where each amplitude and phase of that antenna element you are able to control, and you are able to make a null towards the direction of this object wireless system, which is creating interference for you, so that if null you are able to orient in this direction, then minimum interfering signal will reach to this antenna and will be able to disturb to you. So radiation pattern and other characteristic of antenna are very important to have a proper communication in for the IoT. It is you know, it is a electronically very crowded systems with lots of sensors, you know, wired, and most of the time wireless sensors are used to access the data remotely or wirelessly. You should be able to appreciate what is the basic role of the antenna. Okay, so here that antenna and IoT, you know, these are the various wireless, you can say that protocol or wireless systems for which you need to access them for the IoT, this thing for the under the IoT environment or for IoT application. Here you have UMTS, 2G, 3G, 4G, 5G. Here they are organized in the ascending order of frequency. You have wireless local area network, then microwave multi-access systems, Wi-Fi, everyone knows. I mean, most of the rooms are these days are Wi-Fi enabled, so that you don't require any direct wired connectivity for your computer, and you are able to access internet through I mean, in your computer wirelessly. You have hyperland. Zigbee is the very strong platform, I mean, that most of the time it operates at 2.4 gigahertz. And then here you will be able to have this one as a receiving or transmitting, as well as a node, where you can jack up the much higher power, so that the range can be increased. And then of course RFID, I mean, most of the warehouse or these malls and all, costly items are tagged, and there will be one interrogator or reader unit, or few of them will be located, and then each component which are tagged, that which tag will upon interrogation from the what do you call that, interrogator, or you can say that system from where you are radiating, you are able to communicate with each costly item in the that warehouse, or you can have in malls, so that if someone wants is trying to lift it away, that it is being taken away, so that is also very strong ingredients of this IoT. So these are the protocols which IoT uses. Then accordingly antenna has to be designed. Then many times mobility with low and high dynamics, like if you have a toy which is moving, and then you have to control that wirelessly, or some sort of other gadgets where you try to find out the location and what is the speed through the Doppler shift. That also how the mobility of any objects are ascertained in IoT. From antenna point of view, deployment is very important. How you put your antenna, so that if it is for broadcasting purpose, so that it will have maximum radio coverage. It will be able to have the signal in all the direction. If you want to have a wireless connection between 2 points, then you need not illuminate in other direction. So some sort of pencil beam or like a torchlight beam you can have, so between the transmitting and receiving station. And of course, if you are designing some antenna for broadcasting, and then you are deploying in a place where there is a reflecting surface nearby, so behind that reflecting surface the signal will not reach. So then if you are looking for the broader coverage, RF coverage, then you should see to it that how it is being deployed. There should not be reflections around. Or if you want to have from the broader beam antenna, if you want to direct the signal in the desired direction, so then you intentionally use some reflecting surface which are present in that room, and you deploy the antenna in such a way that broader beam will get converted because of the reflection. It get converted into some sort of directive beam. So deployment of antenna is very important. Most of the time we want radiation pattern of the antenna should be unhindered. It should have as original radiation pattern as that of the isolated antenna, so that you have to take care of the surrounding in such a way that for the desired application, antenna's radiation pattern is used effectively. So deployment is a very, very important parameter, because we use these antennas for in the environment where we have multiple reflections. We have lots of other sources working nearby, so lots of interference you have to use. I mean, you have to bear with, so that you have an antenna which will get minimally interfered. So that underlines the deployment aspect. And of course, now miniaturization is the key word, mantras for all electronic systems, and that automatically gets applied to wireless system as well. So we want for the better mobility, for better handling, for better transportation, we want our wireless system to be as light as possible. So accordingly, the antenna size also has to be as light as possible. So lightweight, so that indirectly tells that you should have a smaller antenna, and then we try to minimize or to make it cost effective, and then also to make it efficient wireless system. We try to have many channels embedded into single antenna, or multi-band operations, that instead of using many antennas for many different applications, we can have different antennas for different frequency band. You will require a large number of antennas, so instead of doing that, if you use a single antenna which will have very wide band, you know I mean wide band, then that single antenna can cover most of these that wireless requirement. Single antenna can work for your various mobile band and various wireless that communication band. So either wideband, and when you require large isolation between two that frequency band, then instead of wideband you require dual band, triple band, or multi-band, so that their interference between two channels which is using different band is minimum. So that also one has to design an antenna such a way that either you can have wide band, so that 10 different functionality can be effectively realized using single wideband antenna, or maybe a multi-band antenna, where you require isolation between various bands. So for all these applications, choosing the right type of antenna is very, very essential, which will meet all the requirements of this for the IoT application. So that is these are some of the functionalities you require for the that what do you call for IoT antennas. Now we will now slightly deviate and try to at least for next maybe 20 minutes or so, we'll briefly describe the basics of the antenna. So we will start with the basic definition of antenna. Then what are the characteristic of the antenna? Bandwidth is a very important parameter, and that is associated with the terminal of the antenna, input impedance of the antenna. So that we will see the definition. So bandwidth, input impedance, radiation resistance, all these things are the terminal characteristic of the antenna, where you consider antenna as a circuit. Whereas when you take antenna as a transition between guided wave and free space wave, then we talk about the radiation characteristic of the antenna. In that we will see the radiation pattern, and from the radiation pattern all these parameters which are listed below, like beam width, gain, directivity, front to back ratio and efficiency, these things can be derived. There are many other parameters are there for the basic antenna, but then we are limiting ourselves only for to the parameters of the antenna from the IoT point of view, IoT application point of view. Now, for briefly, I will go to the I will go away from the PPT, and then we will use the basic board and chalk here. Now, if you see the basic definition of the antenna, uh, we are talking about uh, antenna as a component. One second. An antenna as component. Then we define antenna from its functionality. Otherwise some of the original definition of the antenna doesn't hold good in the present days scenario. If you see the definition of the antenna, IEEE or dictionary definition of the antenna, it is defined as the device generally in the form of metal, which is used for transmission or reception of electromagnetic wave. That is the basic definition of the dictionary definition of the antenna. It is some sort of metal objects used for radiation and reception of radio waves. That is the dictionary definition. But in present day situation, we are also talking designing a dielectric antenna, dielectric rod antenna, dielectric resonator antenna, DRA, or in that matter even the slot antenna. Slot can be the deformities, or slot can be put in dielectric, it can be put in metal. So those type of the new antennas, like dielectric antennas, they are not covered by the basic definition of the antenna. If you talk antenna as a metallic device, some sort of a metallic structure. So if you try to understand the basic function of the antenna, thereby you define the basic the definition of the antenna. You have generating a signal you want for the wireless communication. So this antenna is used here to launch the signal in free space, and then that is for transmission. And similarly you can have for the reception, where the reverse function is repeated. Here you from guided wave, the signal in guided wave form in a transmission line is getting launched in free space, and then to facilitate wireless communication here. So then this antenna can be defined in terms of transition between guided wave and free space, or you can define in terms of transducer guided wave. One form of energy is getting transformed to another form of energy, transducer, or guided wave impedance is getting transformed to free space wave impedance. So it's an impedance transformer. So these are the transitional definition of antenna. Okay. Now, if you see these that line of sight communication which I have drawn here, you can see that this antenna is radiating in this direction, and that radiation is reaching to receiving antenna. Thereby, the signal is transported from the transmitting antenna to receiving antenna here wirelessly. So when you are focusing so antenna can be defined as focusing device, which is focusing electromagnetic signal in the desired direction. But at the same time, when you say this is the desired direction, then all other directions are undesired direction. So from that point of view, antenna works like a spatial filter. It is doing filtering in space domain, uh, spatial filter. So you try to maximize the signal strength by making these things more focused, this radiation pattern in the desired direction. Thereby you are minimizing the radiation in the undesired direction. So antenna is that way doing the job of filtering in space, passing the signal in the desired direction, minimizing the signal in the undesired direction. So this is very, very important definition. It is not a classical definition, but very important definition pertaining to IoT, also for mobile communication, and smart antenna concept. All these things they use filtering in space, so that is the spatial filter. And of course antenna is a resonator, because when you say you are designing monopole lambda by 4 at given frequency, so it will respond to the given frequency, it will not respond to other frequency. So frequency selectivity comes here. So that's why we call it as a resonator, or you can say electrical filter. So all these things are uh, the definition of the antenna. There are many other definitions which we are not touching here. We are only talking about those definitions which are relevant for IoT. Now, coming back to the next, these things, coming back to the next definition here, that is bandwidth, radiation pattern, gain, efficiency, and front to back ratio. So if you uh, see that other parameters of the antenna, uh, see antenna here, you can consider from two, the basic main consideration is that this transmission line, this portion of the transmission line, you can see that you are connecting from the source which is generating a signal which you want to radiate wirelessly, and then you have here connected to antenna. Now here, this transmission line is getting terminated by input impedance of the antenna. So here, this antenna, this structure is being replaced by this impedance, which is input impedance. So this is the terminal impedance of the antenna. Now, this terminal impedance associated with this one, lots of parameters of the antenna are defined. That is known as terminal characteristic, terminal parameter, or terminal characteristic of the antenna. So here you can have input impedance. These are pertaining to IoT. So we will see that, try to link this one. So input impedance, accordingly you have a return loss, you will have VSWR, or you can have input reflection coefficient, how efficiently the power is being fed to the antenna, and minimum reflection or loss, return loss will be there because of the proper matching at the input of the antenna. And accordingly, we define that frequency range over which antenna behaves satisfactorily, and that frequency range is known as the bandwidth of the antenna. So we define the frequency range over which your VSWR remain less or equal to 2, or only 10% power, maximum of only 10% power gets reflected back, and 90% power is getting radiated, so all these parameters are related with the terminal characteristic of the antenna, input impedance of the antenna. So that is the basic definition of terminal characteristic. Now, other things which you just saw here is are the radiation characteristic of the antenna, radiation pattern, beam width, gain and directivity, front to back ratio, and efficiency. So we will quickly see those things. Now here, if you are directing the radiation in the desired direction from the antenna. So if when we have the antenna which we want to from which we want to direct the beam in this direction, and all other direction we want to have main these things. So if you plot the radiation that characteristic with three dimensional these things from all different direction, angular three-dimensional angular spread of radiated power is known as radiation pattern. So here the beam is maximum. So then we say that gain of this antenna is maximum. We say directivity of the antenna is maximum, and then when efficiency is 1, then directivity of the antenna is same as the gain. So if with respect to maximum radiation, if you try to find out the half power and then find this angle, so then this is known as beam width of the antenna, beam width. So this you can consider this structure as a balloon, three-dimensional balloon. So you will have beam width in two principal plane, like a balloon. If you cut in two perpendicular plane, whatever that projection, that 3 dB projection, what you get in with respect to angle, that becomes the beam width of the antenna. So this is known as main lobe of the antenna, main lobe. And all other these are side lobes, that is not the main lobe. We want to have a minimum radiation in this direction. So other this thing is, when we want maximum radiation in the desired direction, then we want for most of the application we want minimum radiation in the backward direction from this antenna. So the ratio of this maximum radiation in the front direction with respect to the back radiation, that is known as front to back ratio, FTBR. That's what here we have seen the last parameters here is front to back ratio, so that is the meaning of front to back ratio. Now so these are side lobes, and these are the nulls, where the minimum radiation is there. These are the null positions. You can say that these are the null position. So if for antenna, if some interfering signals are very strongly coming, definitely you don't want interference from the main lobe direction, because along with the signal, that interference will also put that. But some interference which you cannot avoid, then what you do, you customize your radiation pattern in such a way that you have null in the undesired direction, so this is the basic characteristic of gain of the antenna. Now, any directivity of the antenna is generally given by 4 pi. You have half power beam width in E plane in radian, not in degree, and half power beam width in H plane in radian. So that is basically known as directivity of the antenna. Now, if gain of the antenna, directivity is with respect to the total radiated power, whereas gain is with respect to the total input power. So, efficiency of the antenna multiplied by directivity. So this is the meaning of the gain. And this, when E efficiency is 1, this efficiency is E is 1, then directivity will be equal to gain of the antenna. And in that case, gain of the antenna is directly related with the area of the antenna divided by lambda square. So we took A by lambda square as the electrical area. That's why for a smaller antenna, you will have the gain, lower gain, and for larger antenna like parabolic dish antenna or even array antenna, your area, electrical area will be large, so your gain and directivity will also be large. So these are some of the basic definition of antenna. Pertaining to any other definitions we have missed: gain and directivity, radiation pattern and beam width, front to back ratio, efficiency, beam width, antennas, all those things we have covered. So these are some of the characteristic of antenna for the application of IoT. So that now we will come to the so now we will proceed further for today's this thing. So this all these things we have covered. Now the next one is this we have already seen. Now we will come to what are the design challenges when we talk about designing the antenna for IoT application. As now you will be able to appreciate that how there is a contradicting requirements, for the IoT antennas. Like I said, this is a miniaturized world. When the mobile phone was first introduced, the size of that mobile phone was bigger than a room of dimension 5 meter by 5 meter. That big was the mobile phone. Of course, that was mounted in a truck, and then people used to take that one from one point to other point. So that's why it was known as mobile phone. But now you see your with many more, maybe millions time more functionality, your size of the mobile phone is not even 5 centimeter by maybe 10 centimeter. I mean, that is the size of the antenna. So you can see what is the scale of miniaturization. Likewise, most of the things we want handy, I mean, so the size of these wireless systems used in IoT, their footprint is shrinking. So is the footprint of antenna, because you cannot have a smaller electronic gadgets with big protruding antenna coming out of that one. So then you would like to have smallest antenna for the IoT. Now you have just seen that area of the antenna is direct function. I mean, gives you that gives directly the measure of the gain of the antenna. We want maximum gain in the desired direction, and you cannot have larger gain with a smaller antenna. smaller antenna. These antennas, these two parameters, that a smaller antenna means shrinking footprints with superior performance. Also, that is a requirement. You try to make the antenna size as small as possible without sacrificing the electrical performance of the antenna, and that is next to impossible. So that is how these days smart designs are coming up, smart materials, so that you try to have a minimum loss, so that whatever power you are feeding to antenna, without any loss, will get radiated for intended radiation pattern or intended application. That is one thing. Second thing, when you are making a smaller size, so naturally a smaller size, so gain will be less. And so if gain is less, then your beam width will be larger. Broader the beam, smaller is the focusing effect, so less will be the beam width. So from that type of this first requirements also has a bearing on that pattern maintenance, requiring large, higher gain in the desired direction with miniaturized antenna. So maintaining some pattern for this shrinking footprints, from the shrinking footprints of the antenna, becomes very difficult. Next one is gain maintenance. You require, like, these two are interlinked, that how you will be able to maintain the higher gain with the smaller antenna, and also not only smaller antenna, you will also have uh, what do you call, that you have to mount that one in the electronic system. So in that case, then your pattern has to be maintained. You presence of that structure on which you are mounting should not modify the radiation. Of course it will modify the radiation pattern because it is becoming bounded media, but it should not modify that much that you, instead of having a main lobe in the desired direction, you should not end up having a null in that direction. Shrinking footprint and electronics crowding also puts lots of challenge for maintaining the radiation pattern and gain for the intended application. Next one is coverage. If you have come across that freeze equation or wireless equation, gain of the antenna plays a very important role. PT, GR, lambda divided by 4 pi whole square. So that is the equation. So when your antenna reduces, antenna gain reduces because of the shrinkage in size or because of mounting that one in certain structure, then your range or coverage of the antenna also gets limited. So that is another point that has to be kept in mind. Other one is that RF power harvesting. So many times, in many remote places you don't have electricity. So what you do, but then now RF power is omnipresent everywhere. You will find certain RF power, distribution. So you can use receive that RF power, pass through that one through the detector and voltage doubler, so that you are able to generate some sort of that the voltage, and that can be used to drive or power your wireless system or mobile phone. So for that also you require a larger aperture area of the antenna. So again, requirement here, and then shrinking footprints are contradicting in nature. Other thing I said that it is electronics crowding that is taking place. Earlier, that space used to be less occupied by RF signal. Only somewhere some radar is operating, or radar from the airport are operating. And this matter, in that matter, somewhere some army establishment is there. Those RF signal or broadcasting, though earlier TV stations, the radio stations were there. Later on, these TV stations also came into picture. So all those things slowly have started. Now mobile phone, every nook and corner we have mobile, these things, and that also now to have to minimize the cold drop, various diversity techniques are used for this one. So reconfigurable antennas and all those requirements are coming, so that we have to adapt to the extreme interfering scenarios, so that in this case also our antenna for wireless application should work, for antenna for IoT should work. And then also there is compliance requirement will be there. EMI, EMC, we see that RAID, what do you mean by RAID, or SAR compliance, all these things, compliance has to be made by these IoT antennas. So that your antenna has to be designed for these applications also. These are some of the common footprint of antenna. First is that as small as possible for most of the application, except for the applications where you have the base station, or you are trying to distribute your signal in all the directions, so that nearby all wireless system will receive those signal. Except for those scenario where you use array of antennas, most of the device based antennas are very small, very small. So that is what you can see here. You have a small metal patch antenna. You can consider this as a sort of handheld dipole antenna, or you can have a loop antenna. You can see these things. These are some of the dipole antennas which are there here. So these are the small footprints of antennas. In this case, it is a monopole antenna. You have dipole antenna, you have patch antenna, you have wire antenna, I mean coaxially fed here dipole antenna. And you should be 2D or 3D integrable, I mean, these antennas, any electro wireless system will have its 3 dimension. Though we are making it miniaturized, nevertheless it will have 3 dimension. These are 3 dimensional structure, or it will be on the surface. So that's why on the surface, when you are mounting an antenna, it is that 2D integration, and in 3 dimensional when you are mounting this, there is this 3D integration. You should be able to integrate your antenna in such a way that it should remain, it should have desired radiation pattern. The body at which you are mounting should not deform the radiation pattern, so that you are able to do intended that functions from the antenna. So this is very important. And then input impedance, in the case of in the bounded media, has to be there, so that that modified input impedance will match to the transmission line. There, otherwise you will lose lots of power in the form of reflection from here itself. Instead of radiating full power here itself, if it is not properly matched, not properly integrated in the bounded media, in the interfering media, then you lose lots of power in reflection, because input impedance gets modified, and then only remaining power you will be able to radiate for intended application. So these are very, very important aspects of these antenna, these things. A smaller footprint. puts lots of stress on antenna designer, so that you still you have a small device, but at the same time you are able to meet most of the electrical requirement. So that is the basic design point for these IoT antennas. Other these things is you have to orient in such a way that in the multipath effects, and then lots of reflections and highly interfering environment, you have to look in such a way that there is no polarization mismatch. So you can see that here it's a dipole antenna with a donut type of radiation pattern, and it is vertically polarized. So your this antenna, which between these two, if you want to have a wireless linkage, then this polarization and this polarization are matching. So you will be able to receive or radiate for proper reception, because polarization is matching. Now when polarization they are crossed, this is vertically polarized and this is horizontally polarized, then there will be zero reception, though you are transmitting very high power. So this will not work. So this maintaining the polarization in the multi-source, multi-path scenarios also is a very important aspect. So that also has to be kept in mind, and also this will have bearing on how you are mounting. So this is another aspect that you have to take care. And then third one is you have to maintain the gain. Like in PCB antenna, you can see here this FIFA antenna is printed. FIFA antenna is shown here. So here you have to you are mounting that one in a PCB, or you are fabricating that way in PCB. If you want the coverage, all around coverage, then you cannot have a ground plane. So then you cannot call this as a microstrip antenna. If you are removing the ground plane in the backside direction, then at most you can call this antenna as printed antenna. you know but when you want to cover only half hemisphere on the top side in the space, then you can say that you can still you use a microstrip configuration, so only the radiation will be confined in the in the up direction, because ground plane is there in the back direction. So again, you have to miniaturize. So you cannot have an infinite long ground plane. You need to have a minimum ground plane, finite ground plane. So in that case also, then certain amount of radiation will go in the undesired direction, in the back direction. So when you are integrating you as an integral part of any PCB, when you are designing the antenna, couple of things has to be kept in mind. What is the coverage, total coverage required? Total coverage means what is the total direction in which you want to communicate from this PCB antenna or your this PCB system. And that is one thing. Second thing is that what will be the front to back ratio you are looking for, what is the matching these things you are looking for, because you don't have an antenna in free space. So in guided wave structure, you are because here dielectric material is there, so naturally you have to take account in such a way that in presence, when you are printing in dielectric material, you have reasonably good matching input impedance with other integrated component which you have integrated the input of the antenna with other PCB subsystem. So this also is important, maintaining the gain in this PCB integrable antenna or printed circuit antennas is also one of the major challenge. Now, this is the present day. If you have a smart house and you want to know that which who is sitting where right now in a given time, or whether a storage of food grain in the house is enough, so you have put a suitable wireless sensor there also, or you have put a camera so that you can wirelessly monitor through that camera the various that things which are there located at various places, or inside you have that Wi-Fi environment, so that you are able to you have connectivity wherever inside the room where you are moving, or most of the doors, if someone is knocking the door, automatically wirelessly the door gets open. So all functions which are done inside the house can be managed wirelessly, I mean, through this the concept of IoT. And if someone is sleeping here and he's not able to get up, but then he want to take deliver the lecture to other continents, so that then he will be able to sit from his place. He should be able to access all the electronic gadgets and then deliver the talk. So all these IoT enabled house, or you can say smart house, has got electronics crowding. So you have to take care of the extreme interfering scenario. You have to see to it that these all that functionality of various electronic gadgets, they work satisfactorily even in the presence of extreme interfering signals. So designing the antenna, and at the same time you cannot have a big phased array antenna. You cannot have. So with the smallest antenna, you should be able to cope up with these extreme interfering environments. So that puts the concept, I mean, though it is looking I mean, trivial thing that you have a smart house, but then lots of circuit design, electromagnetic design, and then lots of that signal enhancer, signal suppressor, undesired signal suppressor, all those things has to be used in such a way that each one of your subsystems are electromagnetically compatible, I mean, in this situation, and they are hardened to work in this extreme interfering environment. So that is also one of the major challenge. And yet your antenna size should be as small as possible. So this is a designing a phased array antenna for strategic application, where you have lots of, you can assume the environment is more or less unbounded environment, is rather, I would put it this way, is rather simpler than designing a small antenna for IoT. So that type of design challenges are there in this case. Now, so unwanted harmonics has to be dealt with. When you have inside the house, let us say you have 100 wireless systems or sensors which have been put there. Now, so that much electronics crowding is there. Now, most of the time, we approach I mean, for some critical application, we approach WPC, or WPC has earmarked some frequency band which you can use, or unlicensed band you will be able to use. You don't require clearance from WPC. So most of the time we focus our attention in antenna design for the fundamental mode, and we are not much concerned about the separation of the harmonics which this antenna is generating. Though you have designed for the fundamental mode, as I said, antennas are resonators. So resonance means it will have all harmonics and serve harmonic resonances. So in that case, you have to design in such a way that it will work very nicely for the fundamental mode. At the same time, it should suppress your harmonics. So that is another major challenge for the designer. Okay. Now the next very important point is that compliance. You have to you make your systems EMI hardened or electromagnetic compliant. So some of the things which here I have put is EMI, EMC, RAID, and SAR compliance. So for that one, like is that recently one term was introduced, that is RAID. That means Radio Equipment Directive. So that has to be complied for the European countries. Likewise, you have European Electromagnetic Compliance EMC directive. So that also has to be complied. So basically, your antenna should work in a very, very intense that electromagnetic interference environment, and you should be able to design your antenna in such a way that it works properly for the work properly in the uh, very high level of interfering signal. So before you use those antennas for your system, you need to test for the compliance, whether harmonics are getting suppressed, whether your antenna is hardened. So that has to be that compliance has to be looked into. Someone was asking me what type of antennas are used. So designing an antenna for IoT, you have come across cheap antenna. Basically they are loaded monopole antenna and fed by microstrip line. So those antennas are very small size. Even if you are using at lower frequency, you should know the rule of thumb that antenna can radiate or receive efficiently if its size is comparable to the wavelength. So at lower frequency, wavelength is very high in meters or sometimes hundred of meters. In that case also you have to make your antenna small size. So some sort of meanderance is used, some terms of winding is used, some loading mechanism has to be used so that it is a small size even at lower frequency. And reliability aspect has to be taken into consideration because they are working in highly interfering environment. So you should be able to reproduce the antenna for the given characteristic, you know proper matching. So that is also very important parameter. And so instead of seeing only at one particular frequency or one free space environment, you have to take that mid-range performance, and mid-range, and also it has to be cost effective. So that is the cheap antenna. Then you have variety of wire antenna, dipole, monopole, loop antennas. All these are this monopole antenna, and they are highly cost effective. So because you use only the wire, so low PCB. So for that also you have to design, and then you can see that here that a monopole has been meandered. Otherwise, the length, stress length will be a quarter wavelength. So instead of that will take much larger this thing that will protrude out like this, like whip antenna. So instead of doing that, you have meanderance. so that your electrical length you are not compromising. It is lambda g by 4, or if you are designing a dipole, it is lambda g by 2, so that your performance is reasonably good, and you use a miniaturized technique for this type of antenna. Then you can have whip antenna. These are known as, they are nothing but loaded monopole. They are loaded so that this length you are able to reduce. So they are highly cost effective. Very good performance you can have because they are protruding out, so they sees that clear cut free space environment, and they you can directly coaxially feed them. You will be able to directly feed that one. So here coaxial connection require, I mean here connectors are required, so it is slightly that size becomes larger, and it become, because connectors are required and then you are doing loading, so it is costly as compared to simple wire antenna or PCB antenna. PCB antenna, printed circuit board antenna, generally for most of the application we use glass epoxy, that is very cost effective substrate. So PCB antenna means you are printing in a in dielectric, in glass epoxy substrate, or we call FR4 substrate, whose dielectric constant is between 3.8 to 4.8. So that's why it is known as FR4. Dielectric constant is average dielectric constant is around 4. So low cost is small size at high frequency, easy to EM simulate, because lots of these things are there, simulators for PCB, or I3D like simulators for 2D structures. Performance challenge at lower frequency, lower than 500 megahertz, it has got lots of design challenges because wavelength is much larger here. So a dedicated space on PCB required, so that you are not able to do miniaturization when you are putting an antenna there itself, because antenna has to radiate, so it's all other metal, these things should be kept as far away from here, otherwise there itself power will get coupled. So these are some of the antennas which are used for IoT, and this summarizes the frequency band for various band used for IoT technology. So you can see Zigbee 915 and 2.4 gigahertz is used. Similar Z-Wave is there. Then Bluetooth 2.4 gigahertz. Wi-Fi uses variety of frequency 2.4, 3.6, 4.9, 5 and 5.9. GPS has got fixed band with fixed bandwidth. Then wireless HART, that's 2.4 gigahertz. Like that you have that wireless area network. You have got various frequency band. There are medical, because IoT you can have medical applications, so these frequency bands are used for that frequency. These are allocated by WPC. WPC means Wireless Planning Commission, that is the full form, which comes under Ministry of IT. Now it is Ministry of Communication. So that one uses this frequency band, and then for avionics 4.2 to 4.4 gigahertz are used. So these are the things, sort of overview type of things I thought I'll present for the IoT antenna. Now in next maybe 5 to 10 minutes I can take up some question if there are any doubts or any question. Hello.
Yes, sir. There is one question.
Yes.
From Samiran Chatterjee. What is the meaning of SAR?
He might be thinking specific absorption rate.
Samiran, if you are there, please ask the question to sir.
This many of the abbreviations, you do Google search. Sometimes it is very, very difficult to know, because various countries they use various abbreviations. So some like RFID, radio frequency ID. Some I saw some paper which was IDRF. You know so there are variations. So my suggestion is that whatever abbreviations you do Google search, you will get quick answers, because for India,
Sir, sir.
yeah. So my
No,
suggestion is that
well,
for is so
sir, can you hear me?
my suggestion is that you do Google search. Uh, it is
Yes, yes.
your sound is breaking.
So,
Hello.
sir, actually, the thing is that for this
Not,
TSA is necessary for IoT.
nothing. Huh?
TSA is necessary for IoT.
I'm not able to answer
Sir,
your.
can you type your question because your voice is breaking?
See, if I gather what you are saying, that specific absorption rate, because, like, let us say that you are using mobile, I mean, that is also you can see that wireless application of IoT, you are able to access the data, and I mean, so in that case also, how much. If you are asking from that specific absorption rate, I mean, all these things, our human body is exposed to all these radiations, so sometimes there is guidelines that it should not exceed the permissible limit, and permissible limit is for the radiation for human body is 1 milliwatt per centimeter square. That is calculated from the assumption that your body temperature, because of absorption of RF signal, should not increase more than 1 degree. So it has got direct implication. But my suggestion is that any abbreviation, if you have any doubt, kindly see, directly type and Google search you do. Use IoT application. That will be the real meaning of IoT application. Yes.
Uh,
Next
okay, sir.
question.
We have the next question. How
Yes.
to simulate and validate antennas for IoT?
See, I mean, you don't have this, like you see the feature of the antennas for IoT, I mean, it has to be as small as possible. It should be as compact as possible, except for those baseband application. Generally, you go for array there, but then any that device or sensor will require a smaller antenna. So they are much easier than that. First, you have to see the specifications of the antenna, and then you can choose. You had four choice here, chip antenna, wire antenna, you have whip antenna, and then you have PCB antenna. So depending upon, or you can have microstrip antenna if you want to restrict your radiation in half hemisphere. So in that case, then you have to take the characteristic, and then there are rule of thumb. You have various handbooks which are there, and lots of papers people have on these four type of antennas, which are generally known as IoT antenna elements. And then it is much simpler. Basic physics or electromagnetic behind the design you should know. Like most of these antennas has got omnidirectional radiation pattern, means it covers in one particular azimuthal plane, it will be omnidirectional. So designing these antennas are not very difficult. Even if you take a small wire and then load that wire, make it loaded lambda by 4 is smaller antenna, make thicker these things, and then the characteristic of monopole antenna. So But these days lots many simulation tools are there. You can use those simulation tool. First you make the structure, and then you excite that structure, find the various parameters, and then you know the characteristic of the antenna.
Okay, sir. Sir, the next question is PFA is required for IoT.
What is that?
PFA is required for IoT.
PIFA antenna you were saying?
I think the
Yeah, inverted AF antenna, that is
yes,
known as printed inverted AF antenna.
yes,
See,
sir.
printed inverted AF antenna is nothing but loaded monopole antenna, you know. And yes, I mean, people use PIFA antenna for IoT wherever you have radiation pattern corresponding to that loaded monopole antenna. You can use PIFA antenna for IoT.
Okay, sir. The last question is what type of antenna we can use for wearable medical device telemetry?
See, these days, wearable, lots of people are doing research on wearable antenna. You know, I remember one professor from eastern part of our country had gone to Weaver, and he wanted to make that metal ujadi ka kaam hota hai. So there itself he wanted to make a patch, you know, on that silk background, and then you can use that simple exciting technique to, so that wearable antenna itself will radiate. So it depends. You have wearable antennas, you have conformal antennas. That depends on what medical applications you are looking for. If you want to measure the blood all the time, want to monitor the blood pressure, you can use a conformal antenna or a small chip antenna which can be attached with your body. So it pretty much depends on what application you are looking for. If you want to monitor the temperature of your body all the time, I will prefer putting a small patch, flexible patch antenna, which I can put on the arm, the hand arm, and then it will continuously with a sensor, so that it will measure that body temperature, and then through antenna it can radiate to nearby base station, through base station, or those that what do you call that wireless medical application. It will get broadcasted where someone who is monitoring the temperature is. So depends on what you want to monitor in human body, you know.
Okay, sir.
Yeah.
So if we don't have more question, can we close for the session? I hope there is no more question. Okay. Thank you very much, sir, for your informative lecture. I hope the participant has been benefited from this.
Thank you, sir.
Hello.
Yes, sir.
Okay, Nagendra Jain.
Okay, sir. Okay, sir. Thank you. Thank you very much, sir.
Thank you.
Okay. So uh, we will be meeting tomorrow at same time, 10 o'clock in the morning. And as I have announced in the previous class, we might be needing five volunteers. For the first class, there will be demonstrating one of the technologies, not in the much detail, but up to the scale that we can we are able to understand. Okay. So thank you, everyone. If you have any question, you please put on uh, the WhatsApp group, or you can either mail me. Okay. Thank you, everyone.